So let's look at the basic concepts of networking, and of course, the mother of all networks, the Internet. The Internet is a global system of interconnected computer networks that use the standard Internet Protocol Suite, often called TCP/IP, although not all applications use TCP, to serve billions of users worldwide. It's a network of networks that consists of millions of private, public, academic, business, and government networks of local to global scope that are linked by a broad array of electronic, wireless, and optical networking technologies. The Internet carries an extensive range of information resources and services, such as the interlinked hypertext documents of the World Wide Web, www, and the infrastructure to support email. The origins of the Internet reach back to research done in the 1960s, commissioned by the United States government in collaboration with private and commercial interests to build robust, fault-tolerant, and distributed computer networks. The primary precursor network, the ARPANET, initially served as a backbone for interconnection of regional, academic, and military networks in the 1980s. The funding of a new U.S. backbone by the National Science Foundation in the 1980s, as well as private funding for other commercial backbones, led to worldwide participation in the development of new networking technologies and the merger of many networks. The commercialization of what was by the 1990s an international network resulted in its popularization and incorporation into virtually, I'd say, every aspect of modern human life. So as of 31st December 2017, more than 4.1 billion people, nearly 55% of the whole world population, use the services of the Internet. Now, I'll put that in a little perspective here. That's 95% of North Americans and about 85% of Europeans are Internet users. Now, before talking about the Internet Protocol, or what we call IP, we should know what a protocol actually is. A protocol is simply a set of rules governing how things work in a certain technology, so that there is some kind of standardization. Protocols are also typically in charge of sending the right data to the right PC, making sure the data gets to the right program, as well as organizing the data to be sent. Protocols are to computers what language is to humans. For instance, this course is in English. To understand it, you must be able to understand English. So similarly, for two devices on a network to successfully communicate, they must both understand the same protocols. So I know we're going to talk about this in detail later, but we'll talk a little bit now about IP to better understand the Internet. Internet Protocol, IP, describes how data packets move through a network. So when you have a protocol, you are sure that all machines on a network, or in the world when it comes to the Internet, however different they might be, speak the same language and can integrate into the whole framework. The IP protocol standardizes the way machines over the Internet or any IP network forward or route their packets based on their IP addresses. So along with addressing, routing is one of the main functions of the IP protocol. Routing consists of forwarding IP packets from source to destination machines over a network based on their IP addresses. An IP address is a unique address identifying a machine, which can be a computer, a server, an electronic device, a router, a phone, you name it, on a network, thus serving, routing, and forwarding IP packets from source to destination. Basically, every computer connected to the Internet is given an IP address by the Internet service provider, and the computer becomes accessible to others via this IP address. So let's see what the Internet looks like on its most basic level. Here we have a home network with a router given by the Internet service provider, or ISP. Remember that modem that's given to you by your ISP. And the devices it connects to the Internet. This is a corporation with a lot of end-user computers and servers as well. There's a public body here, again, with a lot of servers and a lot of end-user computers. Here is a hosting company with a web server farm hosting to their customers. Now here's a cloud provider such as Amazon Web Services, hosting a lot of servers again. And here there's another home, and they're all connected to each other over telecom company routers. Reference models are conceptual frameworks for understanding relationships. The purpose of the reference models are to guide vendors and developers so that digital communication products and software programs they create can interoperate and facilitate clear frameworks that describe the functions of a networking or telecommunication system. OSI, Open Systems Interconnection, is a reference model for how applications can communicate over a network. A reference model is a conceptual framework for understanding relationships. The purpose of the OSI reference model is to guide vendors and developers so that the digital communication products and software programs they create will interoperate and to facilitate clear comparisons among communications tools. Most vendors involved in the telecommunications make an attempt to describe their products and services in relation to the OSI model. And although useful for guiding discussion and evaluation, OSI is rarely actually implemented, as few network products or standard tools keep all related functions together in well-defined layers as related to the model. Developed by representatives of major computer and telecommunication companies beginning in 1983, OSI was originally intended to be a detailed specification of actual interfaces. Instead, the committee decided to establish a common reference model for which others could then develop detailed interfaces, which in turn could become standards. OSI was officially adopted as the international standard by the International Organization of Standards, ISO. So what about the OSI layers? The main concept of OSI is that the process of communication between two endpoints in a telecommunication network can be divided into 7 distinct groups of related functions, or layers. Each communicating user or program is at a computer that can provide those 7 layers of function. So, in a given message between users, there will be a flow of data down through the layers in the source computer, across the network, and then up through the layers in the receiving computer. The 7 layers of function are provided by a combination of applications, operating systems, network card device drivers, and networking hardware that enable a system to put a signal on a network cable or out over Wi-Fi or any other wireless protocol. The 7 open systems interconnection layers are: Layer 7, the application layer. This is a layer at which communication partners are identified. Is there someone to talk to? Network capacity is assessed. Will the network let me talk to them right now? And it creates a thing to send or opens the thing received. Please note that this layer is not the application itself. It is the set of services an application should be able to make use of directly, although some applications may perform application layer functions. Layer 6, the presentation layer. This layer is usually part of an operating system and converts incoming and outgoing data from one presentation format to another. For example, from clear text to encrypted text at one end and back to clear text at the other. Layer 5, the session layer. This layer sets up, coordinates, and terminates conversations. Services include authentication and reconnection after an interruption. On the Internet, Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, provide these services for most applications. Layer 4, the transport layer. This layer manages packetization of data, then the delivery of the packets, including checking for errors in the data once it arrives. On the Internet, TCP and UDP provide these services for most applications as well. Layer 3, the network layer. This layer handles the addressing and routing of the data, sending it in the right direction to the right destination on outgoing transmissions, and receiving incoming transmissions at the packet level. IP is the network layer for the Internet. Layer 2, the data link layer. This layer sets up links across the physical network, putting packets into network frames. This layer has two sublayers, the logical link control layer and the media access control layer. Ethernet is the main data link layer in use. Layer 1, the physical layer. This layer conveys the bit stream through the network at the electrical, optical, or radio level. It provides the hardware means of sending and receiving data on a carrier network. Let's see some of the most famous protocols of the layers. For ease of use, it's better to talk about physical layer and data link layer together. Here we have some protocols in data link layer and some physical media and connection methodologies in physical layer. Ethernet and 802.11 wireless LAN are the most known protocols of the data link layer. Ethernet is the name of the most commonly used network protocol that controls how data is transmitted over a LAN, which is a local area network. You need to have network interface cards in the devices that you want to connect to the network. A wireless local area network, WLAN, is a wireless computer network protocol that links two or more devices using wireless communication within a limited area such as a home, school, computer laboratory, or office building. This gives users the ability to move around with a local coverage area and yet still be connected to the network. Most modern WLANs are based on IEEE 802.11 standards and are marketed under the Wi-Fi brand name. IP, Internet Protocol, is responsible for addressing hosts, encapsulating data into transferred packets, and routing packets from a source host to a destination host across one or more IP networks. The best-known transport protocol is the Transmission Control Protocol, or TCP. It's used for connection-oriented transmissions, whereas the connectionless User Datagram Protocol, UDP, is used for simpler messaging transmissions. We're going to talk more in depth about these protocols in the next lecture. Again, for ease of use, the last three layers, session layer, presentation layer, and application layer, are thought of together as the application layer. Let me put another parenthesis here. We're talking about the OSI reference model here. In addition, there is another reference model called TCP IP reference model. And instead of OSI model's last three layers, there is only a single application layer in the TCP IP reference model. Just keep that in the back of your mind. And back to our subject. The application layer protocols are classified according to the protocol they are using in the transport layer. And these protocols interact with the end user via applications. Therefore, they are the most known protocols by just about everybody. Some of the most well-known TCP-based application layer protocols are HTTP, Hypertext Transfer Protocol, simply a communications protocol used to send and receive web pages and files on the Internet. Telnet is one of the simplest ways to exchange data between two computers. It allows two computers anywhere on a computer network, including the worldwide Internet, to exchange text and, other data in real time. FTP, File Transfer Protocol, is a communication protocol for the rapid, simple transmission of files across a network. SMTP, Simple Mail Transfer Protocol, is used to send and relay an email message between email servers. Note that it is not used to retrieve email messages from a server. Instead, either IMAP or POP is used to retrieve email messages. DNS, the Domain Name System, is a system used to convert a computer's host name into an IP address on the Internet. For example, if a computer needs to communicate with a web server, nhs.uk, your computer needs the IP address of the web server, nhs.uk. It is the job of the DNS to convert the host name to the IP address of the web server. The DNS uses both the UDP and TCP. SNMP, Simple Network Management Protocol, is used in network management systems to monitor status of devices and also spot problems. So let's see what happens to a packet inside the network traffic. Please note, the data unit transferred between two endpoints has different names in each layer. In layers 5, 6, and 7, application layers, it's called data. In layer 4, transport layer, it's called segment for TCP and datagram for UDP. In layer 3, the network layer, it's called packet. In layer 2, the data link layer, the data unit is called frame. Now, I usually use packet for the transferred data unit in each layer to make it less complicated for you. Make sense? Before looking at the road trip of a DNS query in detail, let's look at the relationship between the OSI layers and computer systems. The packets in Layer 1 and Layer 2 are managed by network interfaces of your device, for example, by your Ethernet card. And the packets from 3 to 7 are managed by the processing unit. In software detail, the Layer 3 and Layer 4 packets are managed by the operating system of your devices. And the packets of Layer 5 to 7 are managed by the related application or service, for example, a web browser. When you write a URL in the address bar of your browser and hit Enter, the first thing it sends is a DNS query. A DNS query is the process of a computer or networking device making an inquiry to get an IP address for a DNS name such as mail.yahoo.com. The client computer will send a DNS query to one of their Internet Service Provider's DNS servers. The DNS server looks in its DNS database to tell whether it can answer the query authoritatively. If the DNS server can answer authoritatively, the DNS server answers the query and the DNS query process is complete. So let's see the road trip of a DNS query from your computer to a DNS server. When data is transmitted by the source toward a specific destination, it passes through the application, presentation, and session layers, and the protocol data unit arrives at the transport layer, Layer 4. Layers 5, 6, and 7 are displayed as a single layer to simplify the presentation. At this layer, a 20-byte data header is placed in front of the data. A DNS query can also use TCP, but let's assume that it uses UDP at this time. The data and the Layer 4 header, here it's UDP header, which together form a segment or datagram, is passed down to Layer 3, the network layer. The network layer places its Layer 3 header, here the IP header, in front of the received segment, and this group becomes a packet. The Layer 3 header contains important fields such as the logical address, the IP address, of both the source and the destination device. The newly formed packet is then passed down to Layer 2. The data link layer creates a new data unit called a frame by adding the Layer 2 frame header, which is the Ethernet header here. Like Layer 3, an addressing structure is also applied in the Layer 2 header. That is, the MAC address. The frame is then passed down to the physical layer, which converts the information into 0 and 1 bits that are sent over the physical media using electrical signals, on a copper link, for instance. Finally, the data is sent over the wire using a wide variety of methods such as Ethernet or token ring. The headers are a specific form of control information that allows the data to go through the network properly. Thus, the data at each layer is encapsulated in the information appropriate for the specific layer, including addressing and error checking. The overall size of the information increases as the data travels through the lower layers from Layer 4 to Layer 1. The destination device, which is the DNS server here, receives the data, and this additional information is analyzed and then is removed as the data passes through the higher layers up to the application layer, where the data is decapsulated. The TCP/IP model is a model with 4 layers, which is for both modeling current Internet architecture as well as providing a set of rules that govern all forms of transmission over a network. DARPA, an agency of the United States Department of Defense, created it in the 1970s. This model was being made at the same time the OSI model was created. The TCP/IP model is not the same as the OSI model, however. It was influenced by the model, which is why many of the names of the different layers are the same. So we can simply say that the TCP/IP reference model represents reality in the real world, whereas the OSI reference model represents an ideal. Okay? So these are the main differences of the TCP/IP reference model. The three top layers in the OSI model, that is the application layer, the presentation layer, and the session layer, are not distinguished separately in the TCP/IP model, which only has an application layer above the transport layer. TCP corresponds to OSI layer 4, the transport layer. IP corresponds to a subset of OSI layer 3, the network layer. TCP/IP makes no prescriptions as to the link layers below IP, while OSI specifies 2 layers. The physical address, commonly the MAC address, which is located in a special field in the data link layer header, changes as the packet passes from one device to another. For example, from the source PC to a switch, to a router, to another switch, and then finally to the destination PC. However, the original IP source and destination addresses do not change when transiting the network because the packet is stripped of its layer 3 header only when it goes beyond a router. When it stays within the same LAN, it only passes through switches, which decapsulate it at the layer 2 header containing the MAC address. So as a result, the header changes as the packet is re-encapsulated, as does the MAC address fields. So let's examine the packets and protocols with Wireshark. Wireshark is a free, open source, and it's the world's foremost network packet analyzer. And it's also the de facto standard across system and network administrators. Wireshark has the ability to listen and record traffic, as well as contains some pretty advanced filtering and reviewing options. So first I'm going to visit an HTTP website and then an HTTPS website. Let's go to Kali and run Wireshark. You can open a terminal screen and type Wireshark to start it. So these are the network interfaces that Wireshark is able to listen to. Let me open another terminal screen and run the ifconfig command to see the network interfaces. So as you know, ifconfig stands for Network Interface Configuration. So if we use the command without any parameter, it'll list all the interfaces available. We have ETH0 as a network interface to listen to. So now I'll turn back to Wireshark and double-click ETH0 to select it. Now Wireshark starts to listen to the Ethernet interface of Kali. And to create some traffic, I'll open a web browser and just visit an arbitrary website. And now we have enough packets to examine, so I'll click the Stop button at the upper left corner of Wireshark to stop listening to the traffic. So first, we have some DNS packets to find out the IP address of the visited site. We'll look at these kinds of packets soon, but right now let's just have a brief look. So a DNS query for the IP version 4, another DNS query for IP version 6. Don't worry about the versions right now, we'll cover them soon, I promise. These DNS queries are transferred as UDP packets in transport layer. The destination port is 53. This is the IP packet with the source and the destination IP addresses. So we'll go through the layers one by one, and we'll see all these packets, datagrams, and frames in detail. So we'll keep going. This is the structure of the Ethernet frame. First, there are two DNS queries for www.hackeracademy.uk. One for the IPv4 address, and the other one is for the IPv6 address. And because the website is redirected to hackeracademy.uk, there are two more DNS requests for this address. Next, DNS packets are the DNS query responses. This response is type A. That means it's an answer for the IPv4 request. And here's the answer, the IP address of the website. Now, DNS response packet uses UDP at the transport layer, IP at the network layer, etc. Here we have a TCP handshake between Kali and the web server. We'll also see this in detail later on. A SYN packet, a SYN ACK as a reply, and an ACK packet to complete the handshake. This is an HTTP GET request. We learned the IP address of the website, and now the system is ready to receive the web page. HTTP protocol and application layer. Now you can see the headers and the parameters of the request. TCP protocol and transport layer, source port, destination port, flags, etc. IP protocol in network layer. Here are the source and destination addresses. And Ethernet frame in layer 2. These are the TCP packets, which will build the HTTP response. So in this example, it's the web page. In other words, the response is transferred between the web server and our system as fragmented packets in transport layer. Here's the HTTP response, 200, okay. So the web page is received. And here's the data, which is our web page. These are the response details, response type, headers, etc. Here there's additional information produced by Wireshark, which says that the HTTP response is created by reassembling 5 TCP segments or packets. So now I'd like to show you the difference between that and HTTPS traffic. So I'll go to the browser and visit an HTTPS page now. But before visiting the page, let's start Wireshark. Here's the start button. Continue without saving. Okay, now we have a clean sheet. So I'll go to the browser and hit enter. Wow, lots of packets in milliseconds. So we've got plenty of packets to investigate. Just click the stop button once again. Okay, so the DNS request and the response packets first. Here is a response with an IPv4 address. Here there's a TCP three-way handshake between Kali and port 443 of Google's web server. And now a client hello TLS packet to start the TLS handshake, again between Kali and Google's server. Now to get rid of the other traffic records, I'd like to filter the results by the IP address of the Google server. Now, while the mouse pointer is on the server IP address, right-click and go to Apply as Filter and select the Selected option. So as you can see here in the filter bar, the IP address is assigned as the destination IP address. Now, we only have to see the traffic where the destination is the Google server. But we'd like to see both the incoming and the outgoing traffic. So I'll change the DST part of the filter to ADDR and click the blue arrow to activate the new filter. Now we can see the traffic in both directions. Okay, so here we are at the Hello TLS message. Here are the details of the message. TLS uses TCP protocol in transport layer. The Google server replies a server hello message as the second step of the TLS handshake. Then comes the certificate and server key exchange, and the server hello done message is sent by the server. Kali sends the client key exchange Google server sends the new session ticket, and the encrypted communication starts. Here is some encrypted application data, which is meaningless for others who listen to the traffic. And as you can see here, the message is encrypted at the application layer, so you can still see the source and the destination addresses, the ports, etc. So Ethernet has been a relatively inexpensive, reasonably fast, and very popular LAN technology for, several decades. It was commercially introduced in 1980 and first standardized in 1983 as IEEE 802.3. And has since been refined to support higher bit rates and longer link distances. Ethernet has since become the most popular and probably the most widely deployed network technology in the world. Many of the issues involved with Ethernet are common to many network technologies, and understanding how Ethernet addresses these issues can build a foundation that will improve your understanding of networking in general. So let's keep the design principles of Ethernet simple. The basic idea of its design is that multiple computers have access to it and can send data at any time. If two computers send data at the same time, a collision will occur. And when this happens, the data sent is not going to be usable. In general, both computers will stop sending and wait a random amount of time before they'll try again. Now, a special protocol was developed to deal with such problems. It's called Carrier Sense Multiple Access with Collision Detection, or it might be easier to say CSMA-CD. Today, Ethernet cables look like, thick telephone cables. Modern cables connect to hubs or switches, and each cable runs from a computer's network interface card, the NIC, to such a box. Now, here are the most widely known Ethernet cables. 10-base-2 and 10-base-5 cables are what I would call retro coaxial cables. You don't see them much today. Each computer has a T plugged into it, and cables plug into each side of that T. 10-base-T, 100-base-T, 1000-base-T are all unshielded twisted pair, or UTP cables, which look a lot like thick phone cables, and they go from each computer to a hub or a switch. Initial numbers indicate the supported speed, so the 10 will stand for 10 megabits per second, and 1000 stands for 1000 megabits, also known as gigabit or 1 gigabit. 10-base-F cables are the same as 10-base-T, but they are fiber cables, and they'll transmit light pulses instead of electrical signals over copper. A data packet on an Ethernet link is called an Ethernet packet, which transports an Ethernet frame as its payload. An Ethernet frame is preceded by a preamble and start frame delimiter, or SFD, which are both part of the Ethernet packet at the physical layer, right? There are 4 types of Ethernet frames, and the most common one is the Ethernet 2 frame, also known as DICS frame. We're talking about the Ethernet 2 frame at the moment. Each Ethernet frame starts with an Ethernet header, which contains destination and source MAC addresses as its first 2 fields. The middle section of the frame is payload data, including any headers for other protocols, for example, Internet Protocol, carried in the frame. The frame ends with a frame check sequence, or FCS, which is a 32-bit cyclic redundancy check used to detect any in-transit corruption of data. Address Resolution Protocol, ARP, is a network layer protocol used for mapping a network address, such as an IPv4 address, to a physical address, such as a MAC address. To simulate how the ARP mechanism works, we have a small network in the slide, a switch on top, and 3 computers connected to it. Computer A wants to talk to computer C. It puts an ARP request onto the wire, which happens to be broadcast. Essentially what it's saying is, who has computer C's MAC address? Of course, because it's a broadcast, every system on the network hears it. Does everybody respond? Well, what happens is that B hears that A is looking for the MAC address of computer C. B knows that it's not computer C and therefore does not respond to the broadcast. The broadcast, the ARP request, goes out to every system, but the only system that will reply is computer C with an ARP reply. In other words, computer A says, who has the MAC address of computer C? And although all the workstations hear the question, only C replies and says, I've got the MAC address of computer C, and this is what it is. So the ARP reply sends back the MAC address to computer A, and each of these machines start building an ARP table. So what is the ARP table? Since computers cannot send broadcast messages every time they need to connect with another network device, they store the IP addresses and the corresponding MAC addresses of systems they frequently communicate with in a table called ARP table. All the systems in the LAN maintain this table. The entries in the ARP cache table are generally short-lived and are updated every 15 to 20 minutes. Now let's get back to our topic. Can we say that one of the passive scan methods is just looking into the ARP table of a system, which is a network that we are scanning? Well, sure we can. Inside an ARP table, we see the IP addresses of some of the systems of the network and their corresponding MAC addresses. Let's see the ARP tables in 3 different platforms: Mac OS, Windows, and Debian Linux. We are in a Mac OS operating system first. Open the terminal first. Type terminal in the search box of the applications window, which brings you the terminal application. Typing ARP and hitting enter shows a small help for ARP command. If you want to see detailed help about the ARP command, you can use MAN command. Type MAN ARP and hit enter. You'll get detailed help. A parameter is used to display all current ARP table entries. But hold on, it says A is used to delete all entries as well. How can that be? Well, to delete an ARP table entry, you use D parameter. If you use this parameter with A parameter, you are able to delete all entries of ARP tables. I parameter is used to see the entries of a single interface. By default, ARP command tries to show the display addresses symbolically. To see the IP addresses instead of display names of the systems, you have to use N parameter, which means do not resolve names. Okay, press Q to quit the man page of the ARP command. Now type ARP-AN to see all the entries of the ARP table. Since Mac OS is a BSD-based operating system, the results of the ARP command is displayed in BSD style. Second machine is a Microsoft Windows 8. Let's open a command prompt first. I have a shortcut on my status bar, so I click it to start a command prompt. Alternatively, press Windows plus R buttons, open the dialog box, run Command, and hit Enter. If you type ARP in a Windows system, the help page of ARP command is displayed. Type ARP-A to see the entries of the ARP table. In my opinion, this display is more, human readable than BSD style. Now, although we're not interested in these at the moment, I would like to talk a little about the IP addresses that start with 224 to calm your curiosity. 224.0.0.22 is the multicast address for Internet Group Management Protocol. 224.0.0.252 is used by recent versions of Windows for Link Local Multicast Name Resolution, LLMNR, searching for local network computers. The third machine is our Kali, which is a Debian-based Linux operating system. Open the terminal window. If you type ARP and hit Enter, the ARP table entries are displayed in a human-readable format. As you see, systems are listed with a known domain name such as www.osiref.com owaspbwa.com by default. ARP-H brings you a small help page. If you want a detailed help page, type man space ARP. In a Debian-based Linux system, -A parameter of ARP command is used to see the entries in BSD format, which we saw in macOS. -I is, again, to see the entries of a single interface. Okay, press Q to quit the man page. ARP-A displays ARP table entries in BSD format, and use N parameter to see the IP addresses instead of domain names of the systems. So let's see how the ARP packets are seen in Wireshark. To see the ARP packets, we must first force the system to send an ARP request. Then we can have a close look into the fields of the ARP packets. So I'm in Kali, and I want to look at the ARP table first. So I'll open a terminal browser and type ARP. So this is the ARP table of my Kali. There are two records at the moment, one for the gateway and one for the VM with the IP address of 207. So let's clear the table first. Now I don't have to delete the records of the ARP table, so I can use the H parameter to get help. So it tells me to use the D parameter to delete a specified entry. Now, does it delete all the entries if I don't specify any particular one? So I'll use the D parameter with no value, and it needs the host name. Okay, so I delete the entry for VM207, so I can push it to create an ARP request. Okay, deleted the entry. Now I'll run Wireshark. Now remember, we run Wireshark within the terminal screen just as before. So I'll click Wireshark icon, and that makes it run. So double-click the ETH0 to start capturing the traffic. Okay, now I go to the terminal screen and ping VM207, turn back to the Wireshark interface, and since we have enough packets to examine, let me just stop capturing. So let's look at the first packet. It's an ARP request. When we ping the IP address 172.16.99.207, since Kali doesn't know who has this address, it broadcasts an ARP request to learn the owner of the IP. And the second packet is an ARP response. So I go back to the request and expand the ARP packet information block. The sender MAC address and the sender IP address are Kali's addresses. The target MAC address is filled with zeros because, well, we don't know it yet. When we look at the Ethernet frame, we see that the 48-bit destination address is full of ones. All these F letters correspond to these ones in hexadecimal, and the frame is broadcast, right? Now this is the ARP response by VM207. And as you can see, the VM returns its MAC address in the sender MAC address field to Kali. And then, as seen in the table, Kali starts to send the ping requests to VM207. And then VM207 replies to the requests. Talk about clear communication. So before talking about VLANs, I think it's better to give a brief summary of LANs in general. So a LAN is a local area network. It's a group of computers and associated devices that share a common communications line or wireless link to a server. Typically, a LAN encompasses computers within a distinct geographic area, such as an office or a commercial establishment. Computers and other mobile devices use a LAN connection to share resources, such as a printer or even network storage. A virtual local area network, virtual LAN or VLAN, is a group of hosts with a common set of requirements which communicate as if they were attached to the same broadcast domain, regardless of their physical location. So a VLAN has the same attributes as a physical local area network, or LAN, but it allows for end stations to be grouped together even if not on the same network switch, right? VLAN membership can be configured through software instead of physically relocating devices or connections. VLAN is an important topic and it should be included in this course, but why did I put it in this section, the data link layer? Yes, because VLAN is partitioned and isolated in a computer network at the data link layer. Very good. Let's get into that. In this context, virtual refers to a physical object recreated and altered by additional logic. VLANs work by applying tags to network packets and handling these tags in networking systems, creating the appearance and functionality of network traffic that is physically on a single network but acts as if it is split between separate networks. So let's run down some of the primary benefits of using VLANs. So security at the top. Groups that have sensitive data are separated from the rest of the network. Separating systems that have sensitive data from the rest of the network decreases the chances that people will gain access to the information that they're not authorized to see. Cost reduction. Cost savings result from less need for expensive network upgrades and more efficient use of existing bandwidth and uplinks. Higher performance. Careful monitoring of network use allows the network administrator to create VLANs that reduce the number of router hops and increase the apparent bandwidth for network users. Broadcast storm mitigation. So dividing a network into VLANs reduces the number of devices that may participate in a broadcast storm. Since a principal element of a VLAN is the fact that it does not pass broadcast traffic to nodes that are not part of the VLAN, it automatically reduces broadcasts. Improved IT staff efficiency. That's right, VLANs make it easier to manage the network. When you provision a new switch, all the policies and procedures already configured for the particular VLAN are implemented when the ports are assigned. Simpler company management. Companies may want VLANs set up for departments that are heavy network users, such as multimedia or engineering, or a VLAN across departments that is dedicated to specific types of employees, such as managers or salespeople. Excellent. So a wireless network is a computer network that uses wireless data connections between network nodes. Wireless networks are generally implemented and administered using radio communication. And with this method, the costly process of introducing cables into a building can, well, obviously be avoided. A wireless local area network, WLAN, links two or more devices over a short distance using a wireless distribution method, usually providing a connection through an access point for Internet access. IEEE 802.11 is a set of MAC and physical layer specifications for implementing wireless LAN computer communication. Now, they're the world's most widely used wireless computer networking standards, used in most home and office networks to allow laptops, printers, smartphones to talk to each other and access the Internet without being connected to any wires. So for this, I'm just trying to keep it simple, so I won't talk about the entire 802.11 family or the technical details beneath them. I just want to let you know that the most popular are those defined by the 802.11b and the 802.11g protocols, which are amendments to the original standard. So 802.11-1997 was the first wireless networking standard. But 802.11b was the first widely accepted one, followed by 802.11g and then 802.11n. 802.11n is an amendment that improves upon the previous 802.11 standards by adding multiple input, multiple output antennas, MIMT. So MIMT, it's basically a method for multiplying the capacity of a radio link using multiple transmit and receive antennas. Nowadays, 802.11ac is popular. So it builds on the 802.11n and includes wider channels in the 5 gigahertz band. The segment of the radio frequency spectrum used by 802.11 varies pretty much between countries. For example, in the U.S., 802.11a and 802.11g devices may be operated without a license, as allowed in the regulations. Wireless networks are identified using a Service Set Identifier, or SSID, or I'll call it a SID. An SSID is the primary name associated with an 802.11 wireless LAN, including home networks and public hotspots. Client devices use this name to identify and join wireless networks. Now, there are multiple kinds of SSIDs. Used by itself, the term SSID refers to the name of a wireless network, whether it be a point-to-point network made of only individual wireless clients intercommunicating, or an infrastructure network with clients relying on access points. So getting more specific, we have basic SSIDs, or BSSIDs, which are the MAC address of the access point, the 48-bit number that uniquely identifies every wireless, and every wireline for that matter, network interface. The extended SSID, or ESID, is a unique name applied to one or more access points offering the same service, such as access to a single wireline network. Now, in some deployments, unique ESIDs are applied to each individual access point. In others, all access points that offer access to the same wireline network are given identical ESID values to help foster roaming between the various access points. But generally speaking, when analyzing wireless LANs, we want to discover the BSSID, the MAC address, and the ESID, the name applied to the wireless network as a whole, with a unique value typically applied to each individual access point. Now, since this is a course for penetration testers, we really need to talk about the weaknesses of the wireless network infrastructure. So here are some of the most significant vectors for wireless attacks. Denial of service. Blocking legitimate users on a wireless LAN is trivially easy, even if the network is carefully constructed. Rogue access points. Employees sometimes set up unauthorized access points in an enterprise environment to bypass the legitimate wireless infrastructure, or to gain wireless access when such an infrastructure isn't provided by the enterprise. Now, penetration testers and ethical hackers alike are sometimes required to sweep an organization's physical infrastructure to find these unauthorized access points. Lack of or improper configuration of wireless access points. Right, so if access points are not configured appropriately, attackers can have a much easier time of employing any of the rest of these attack vectors. Traffic capture intercept. In a wireless LAN, the hacker can get access to the data link layer 2 communications, as long as he or she is in physical proximity of the device. For merely capturing packets, that proximity for a wireless LAN could be a mile or more. Numerous wireless sniffing tools can be used in such attacks. Crypto attacks. Some wireless encryption protocols suffer from significant security weaknesses, such as the Wired Equivalent Privacy WEP protocol. Attackers can gather web traffic and, by exploiting flaws in the way cryptographic initialization vectors are exchanged, crack the keys to gain access to the data and the network. Client duping. Some tests call for a penetration tester or ethical hacker to set up a bogus access point to see if clients will trust it and then use it to access the rest of the network. The attacker can then sit in the middle of all the communications, harvesting them or changing the data as it passes by. The next layer is the third layer of the OSI reference model, the network layer. The network layer provides the means of transferring variable length network packets from a source to a destination host via one or more networks. In other words, the network layer is responsible for packet forwarding, including routing, through intermediate routers. Within the service layering semantics of the OSI network architecture, the network layer responds to the service requests from the transport layer and issues service requests to the data link layer. So here are the functions of the network layer. Connectionless communication. For example, IP is connectionless in that a data packet can travel from a sender to a recipient without the recipient having to send an acknowledgement. Connection-oriented protocols exist at other higher levels of the OSI model. Host addressing. Every host in the network must have a unique address that determines where it is. On the Internet, addresses are known as IP addresses, right? Message forwarding. Since many networks are partitioned into subnetworks and then connect to other networks for wide area communications, networks use specialized hosts called gateways or routers to forward packets between networks. Probably the most well-known network layer protocol is, of course, IP, or Internet Protocol. As I mentioned in the beginning of the course, the Internet Protocol, or IP, is responsible for addressing hosts, encapsulating data into packets, or datagrams, including fragmentation and reassembly, and routing packets from a source host to a destination host across one or more IP networks. So like other Layer 3 protocols, IP is connectionless, which means it doesn't care whether the packet has reached the destination or not. That's what Layer 4 is for. All right? So there are two versions of IP that currently coexist within the global Internet, IP version 4, or IPv4, and IP version 6, or IPv6. IP addresses are made up of binary values and drive the routing of all data over the Internet. IPv4 addresses are 32 bits long, and IPv6 addresses are 128 bits long. Right now, we're going to see each of the versions in detail. But before we move on, let's compare the main features of each version. IPv4 is a 32-bit address, and IPv6 is a 128-bit address. Now, theoretically, you can address 2 to the power of 32 devices in IPv4, which is about 4.3 billion, right? In IPv6, on the other hand, you can address 2 to the power of 128 devices, which is, well, let's see. Why don't you just do the math on your own? So IPv4 is represented by the decimal equivalent of 4 octets, separated by dots. The biggest number one can make with 8 binary digits is 2 to the power of 8 minus 1, which means 255. So each octet can be any number from 0 to 255, right? Now, 128-bit IPv6 addresses are written using hexadecimal as opposed to dotted decimal in IPv4. So because a hexadecimal number uses 4 bits, this means that an IPv6 address consists of 32 hexadecimal numbers. These numbers are grouped in 4s, giving 8 groups or blocks. The groups are written with a colon as a separator. Internet Protocol version 4, IPv4, is one of the core protocols of standards-based networking methods on the Internet. It was described in IETF publication RFC 791 in 1981, and it was the first version deployed for production in the ARPANET in 1983. It still routes most internet traffic today despite the ongoing deployment of the successor protocol, IPv6. With IPv4, each address consists of 4 octets. Octet stands for 8-digit binary numbers. So an IPv4 address is 32 bits in total. So that means we can theoretically address 2 to the power of 32 devices with IPv4. So that means the address space of IPv4 is about 4.3 billion. Sounds like it's a big number, right? IPv4 is represented by the decimal equivalent of 4 octets separated by dots. The biggest number one can make with 8 binary digits is 2 to the power of 8 minus 1. That means 255. So each octet can be any number from 0 to 255. Now, also there are special meanings associated with 2 different ending numbers. In general, a last number of 0 stands for the network. Let's call that the base address. And a last number of 255 stands for all hosts on that network, called the broadcast address. Computers that are on the same local network share 3 of the 4 numbers. A computer can be on more than one network, so it can also have several names. So looking at an IP packet consisting of a header section and a data section, we'll see that the IPv4 packet header consists of 14 fields, and only the options field is, well, optional. Now, I'm not going to talk about each field one by one, but I'll give you a few short explanations of some of the more pertinent ones. The version field is always equal to 4. Why? IPv4. The Internet Header Length, IHL field, is the size of the header in words, where word is always going to be 32 bits. The total length is the entire packet size. In this case, it's in bytes. As you know, but to catch you up to speed, 1 byte is 8 bits. The minimum size is 20 bytes, so that's a header without data, and the maximum is 65,535 bytes. The flag is used to determine the fragmentation options. Bit 1 is DF, or don't fragment. If it's set, and I mean by that if this bit is a 1, and fragmentation is required to route the packet, then the packet is dropped. Bit 2 is MF, or more fragment. For fragmented packets, all fragments except the last have the MF flag set. Bit 0 is reserved for the future. TTL, or time to live, is to limit the lifetime of a packet. It's a hop count, basically. When the packet arrives at a router, the router decrements the TTL field by 1. Protocol field is the protocol used in the data portion of the IP packet. So that's going to be TCP, UDP, ICMP. Source address and destination address fields are the most important fields of an IP header. These fields are the IPv4 address of the sender of the packet and the IPv4 address of the receiver of the packet. Please note that this address may be changed in transit by a network address translation device. We'll talk about that later. This is how an IPv4 packet is seen on Wireshark. So it's a DNS query response. The fields we mentioned are seen pretty clearly. Version is 4. Header length is 5 words, which means no options field. Total length is 96 bytes. MF and DF flags are not set. And you can see the source and the destination addresses and all the rest. I know what you're thinking. You're really chomping at the bit to get to subnetting, but before we talk about it, it's better to learn the IP classes and the subnet masks first, right? Octets of the IP address are broken down to provide an addressing scheme that can accommodate large and small networks. So there are basically 5 different classes of networks, and they range from A to E. We're going to focus on classes A, B, and C, which provide unicast addresses for networks of 3 different network sizes. Class D is for multicast networking, and the Class E address range is reserved for future or experimental purposes. So given an IP address, its class can be determined from the 3 high-order bits, and by that I mean the 3 leftmost bits in the first octet. In a Class A address, the first octet is the network portion, so Class A has a major network address of 1.0.0.0 all the way through 127.255.255.255. The next 24 bits are for the network manager to divide into subnets and hosts as he or she sees fit. Class A addresses are used for networks that have more than 65,536 hosts. In a Class B address, the first 2 octets are the network portion, so Class B has a major network address of 128.0.0.0 all the way through 191.255.255.255. Octets 3 and 4, that means 16 bits, are for local subnets and hosts. Class B addresses are used for networks that have between 256 and 65,534 hosts. And finally, in a Class C address, the first 3 octets are the network portion. Class C has a major network address of 192.0.0.0 all the way through 223.255.255.255. Octet 4, 8 bits, is for local subnets and hosts, perfect for networks with less than 254 hosts. So a network masks helps you know which portion of the address identifies a network and which portion of the address identifies the node. An IPv4 subnet mask consists of 32 bits, a sequence of 1 followed by a block of 0. The trailing block of zeros designates that part as being the host identifier. Class A, B, and C networks have default masks, also known as natural masks, and these masks are 255.0.0.0 for Class A, 255.255.0.0 for Class B, and 255.255.255.0 for Class C networks. So an IP address for Class B network that has not been subnet would have an address mask pair similar to 131.107.1.2 being the address, and 255.255.0.0 would be the subnet mask, right? Now, in order to see how the mask helps you identify the network and node parts of the address, convert the address and mask into binary numbers as seen on the slide. So once you have the address and the mask represented in binary, then identification of the network and the host ID is a lot easier. Any address bits which have corresponding mask bits set to 1 represent the network ID. Any address bits that have corresponding mask bits set to 0 represent the host ID. So in this example, the first part, 131.107, is the network part of the IP address, where the rest, 1.2, represents the host. All devices on this segment share the same network ID and the same subnet mask. Now you can customize the subnet mask to divide a network into many smaller portions. So here's a little brain tingler for you. The network ID may be expressed in classless interdomain routing, or CIDR, notation, written as the first address of a network, followed by a slash character, and ending with the bit length of the prefix. So in our example, 131.107.0.0/16 is the prefix of the IPv4 network starting at the given address, having 16 bits allocated for the network prefix and the remaining 16 bits reserved for host addressing. Your patience pays off. Subnetting allows you to create multiple logical networks that exist within a single Class A, B, or C network. If you do not subnet, you are only able to use one network from your Class A, B, or C network, which is, well, pretty unrealistic. So subnetting is the process of designating some high-order bits from the host part as part of the network prefix and adjusting the subnet mask appropriately. So this divides a network into smaller subnets. In other words, in order to subnet a network, extend the natural mask with some of the high-order bits from the host ID portion of the address in order to create a subnetwork ID. So I'll give you an example. Let's take a Class C network of 192.168.2.0, which has a natural mask of 255.255.255.0. You can create subnets by moving 2 bits from the host part to the network prefix. Now, the last octet of the network mask starts with 11. So this 8-bit corresponds to 192 in decimal form. Now the network ID is 26-bit. In CIDR notation, it's now a /26 subnetwork. You can find the network prefix by a bitwise AND operation between the IP address and the subnet mask. The number of subnetworks available and the number of possible hosts in a network may be readily calculated. In our example, 2 bits were borrowed to create subnetworks, thus creating 2 to the power of 2 possible subnets. You with me? So now let's calculate the maximum number of hosts for each subnet. In our example, 26 bits are used to define the network. The remaining bits after the subnet bits are used for addressing hosts within the subnet. So, the host part of the IP address is 6-bit. All zeros and the all ones values for the host ID are not allowed in a subnetwork, right? These 2 values are reserved for the network address and broadcast address, respectively. So the maximum number of hosts which can be addressed in these subnetworks is 2 to the power of 6 minus 2, which equals 62. Excellent. So as a result, the IP addresses of the devices in the subnetwork 192.168.2.128/26 will be between 192.168.2.129 and 192.168.2.190. So, as I mentioned before, the IPv4 address is a 32-bit number, which allows us to address maximum of 2 to the power of 32 devices in theory. That means there are fewer than 4.3 billion addresses available. See where I'm going with this? It's a problem because there are many more than 4 billion internet-connected devices in the world. Desktop and laptop computers, smartphones, smart TVs, smart cars, even smart fridges, smart ovens, the Internet of Things. It's the future, baby. This has led to a shortage of IPv4 addresses. So, my friend and fellow genius, what is the solution to the problem? I think the long-term solution is to switch to Internet Protocol version 6, IPv6. IPv6 has trillions of addresses, enough to give every computer in the world a unique IP address. We'll get into that detail very soon. But the most important effort to migrate the IPv4 shortage is using Network Address Translation, NAT, which allows a private network to use one public IP address, and that permits lots of private addresses in the private network. But wait a second, wait. Private network, NAT, what the heck are you talking about now? I thought you wanted to go to IPv6. Let me explain. Up to now, all the networks that we mentioned were assumed to be a public network, and all of the IP addresses were public IP addresses, right? In the Internet addressing architecture, a private network is a network that uses private IP address space. Wait. I'll try to explain an unknown with another one. But first, I should explain what the private IP address space is. Tell you what, let's take a break here, and I'll talk about the special use IP addresses, including the private IP address space. So the authorities, IETF and IANA, please don't ask. You can Google it if you really want to know who they are. But they've restricted from general use various reserved IP addresses for special purposes. So that means you cannot use any IP address in these reserved blocks as the public IP addresses of your devices. So here we have some of these reserved blocks. Now, these are the most important blocks for us to know, because pretty much anybody who's not familiar with the networking concept gets confused about the difference between public and private IP addresses. So these IP blocks are reserved for private networks. They're commonly used for home, office, and enterprise local area networks, or LANs. Private IP address spaces were originally defined in an effort to delay IPv4 address exhaustion, but they're also a feature of IPv6 where exhaustion is not an issue. Bear with me. Packets addresses in these ranges are not routable in the public internet because they are ignored by all public routers. Therefore, private hosts cannot directly communicate with public networks, but require network address translation, or NAT, at a routing gateway for this purpose. But no worries, we'll talk about NAT coming up next. So without getting too deep, the only thing about the loopback is that 127.0.0.1 is the most common IPv4 address which is mapped to the local host. So let me give you an example. The IP address of your host machine is 172.16.99.222, and a web application is served in your host. Now, in that machine, you can use the web address hhp://127.0.0.1 to access the web app, as well as hhp://172.16.99.222. Both IP addresses point to the same machine, which is your host. Generally, an IP address that starts with 169 means that your computer wasn't able to obtain an IP address from your DHCP server. Usually that means that your router is wedged and needs to be rebooted, or that your Wi-Fi isn't working at all. So now let's have a look at the private IP address blocks closely. As I mentioned a few minutes ago, a private network is a network that uses private IP address space. Administrators of private networks can assign networks and subnets from the above ranges. If an administrator decides to use the IP range 192.168.0.0/16 and then decides to have a single subnetwork assigning 255.255.0.0 as a subnet mask, then he or she will have a subnet with a max of 65,536 devices. Make sense? Okay, I know there are a lot of terms and conditions, so let's just break it down with a real-world scenario. Although the standard for A and B class networks specify 8 and 16-bit masks respectively, it's common to assign non-standard masks for subnets, resulting in much more limited address spaces. Right? For example, using 10.xx.yy.0/24 results in 256 host company subnets, right? So this is done for scalability and, of course, security. Okay, so we're the system administrators in Company X and ready to build. We have decided to use 192.168.x.x as the private IP address space for our company. If we use the natural mask 255.255.0.0, that means we use the first 16 bits for network ID. And we'll have a single network. So in this case, we can address 65,536 devices in this network. Of course, the first IP and the last IP we're not allowed to use, so the number of IP addresses is actually 65,536 minus 2. You do the math. But in practice, for ease of use, it's pretty much used as the power of 2. So you can use an IP address in this network from 192.168.0.1 to 192.168.255.254. But we need to have different networks, one for the managers, one for the developers, one for the servers, etc. So, for the sake of our use and our sanity, let's use the next 8 bits for subnets. In this case, we have a subnet mask of 255.255.255.0. 8 bits for subnets and 24 bits for the network ID in total. 8 bits left for addressing the devices under the subnets. So as a result, we can create 256 subnets and address 256 devices for each one. Now we have 256 address ranges for 256 subnetworks. So the table here shows a few examples of our potential subnetworks. The red colored blocks are added to the network ID as subnet identifiers. The rest of the 8 bits are used as the host IDs. In the 4-block decimal notation, the third block identifies the subnetwork and the last block identifies the host. So, breaking it down, it's much simpler now, isn't it? Excellent. Let's move on. So the private addressing scheme works really well for computers that only have to access resources inside the network, like workstations needing access to file servers and printers and so forth. Routers inside the private network can route traffic between private addresses with no trouble whatsoever. However, to access resources outside the network, like the internet for example, these computers need to have a public address so that responses to their requests return to them. Now this is where NAT comes into play. A workstation inside a private network makes a request to a computer on the internet. The switches or the routers within the network recognize that the request is not for a resource inside the network. So they send the request to the router, let's say the backbone router. Now the backbone router sees the request from the computer with the internal IP. It then makes the same request to the internet using its own public address and returns a response from the internet resource to the computer inside the private network. From the perspective of the resource on the internet, it's sending information to the address of the router. From the perspective of the workstation, it appears that the communication is directly with the site on the internet. So when NAT is used like this, all users inside the private network that access the internet have the same public IP address. So that means only one public address is needed for hundreds or even thousands of users. So let's have a look and see how it works. Here's a typical home network. There's a laptop, desktop PC, a smartphone, all connected to our home router. And the home router is, of course, connected to the internet. So when we register with our ISP, the Internet Service Provider, we get an IP address that is accessible throughout the internet, and that's pretty much assigned to that home router. We refer to it as real IP or public IP. Now suppose that the IP address 20.20.20.20 is assigned to our home router. Our devices inside the home network also have IP addresses, right? But in this case, they get private IP addresses, which are assigned by the home router and are not accessible from the internet. So as you can see here, the public IP addresses are red and the private IP addresses are green. So let's consider a connection request from the smartphone, which requests the homepage of abc.com. So to reach the page, the smartphone has to go through the home router. The packet has the source IP address and the source port address, as well as the destination IP address and the destination port. If it arrives at the web server with these values, it processes the request and tries to send the reply packet to the IP address 192.168.1.5. But that's unreachable for the web server because it's a private IP address. So, when the packet arrives at the home router, instead of sending the packet right over the internet, the home router changes the source IP address with its very own public IP address. It also creates a record in the NAT forwarding table. This table allows us to know which packets will be redirected to the smartphone when they come in. So moving right along, the packet travels over the internet and arrives at the web server. The web server creates a reply packet where the source IP address is itself and the destination IP address is the public IP address of the home router. When our home router receives a response, it looks at the NAT forwarding table and replaces the destination IP and the port according to the mapping inside the table. And finally, the smartphone receives the packet. Pretty cool, huh? IPv6 was developed by the Internet Engineering Task Force, IETF, I'm sure you looked it up, to deal with the long-anticipated problem of IPv4 address exhaustion. So IPv6 is intended to replace IPv4. IPv6 became a draft standard in December 1998 and became an Internet standard on the 14th of July, 2017. So instead of 32-bit addressing of IPv4, which provides approximately 4.3 billion addresses, IPv6 uses a 128-bit address. So that theoretically gives us 2 to the power of 128, or approximately 3.4 times 10 to the 38th addresses. Big number. You can check my math later, but stick with me for now. I mean, the actual number is slightly smaller, as multiple ranges are reserved for special use, or they're just completely excluded from use. But with a rough calculation, the total number of possible IPv6 addresses is more than 7.9 times 10 to the power of 28 times as many as IPv4. The two protocols, IPv4 and IPv6, are not designed to be interoperable, complicating the transition to IPv6. However, several IPv6 transition mechanisms have been devised to permit communication between IPv4 and IPv6 hosts. In addition to offering more addresses, IPv6 also implements features not present in IPv4. Simplified header. IPv6's header has been simplified by moving all unnecessary information and options, which are present in the IPv4 header, to the end of the IPv6 header. The IPv6 header is only twice as big as an IPv4 header because that IPv6 address is 4 times longer. End-to-end connectivity. Every system now has a unique IP address and can traverse through the internet without using NAT or other translating components. After IPv6 is fully implemented, every host can directly reach other hosts on the internet with some limitations involved, like a firewall, organization policies, and stuff like that. Auto configuration. IPv6 supports both stateful and stateless auto configuration mode of its host devices. This way, the absence of a DHCP server does not put a halt on inter-segment communication. Faster forwarding and routing. A simplified header puts all unnecessary information at the end of the header, like we saw earlier. The information contained in the first part of the header is adequate for a router to make its routing decisions, thus making them as quickly as looking at the mandatory header. IPsec. Initially, it was decided that IPv6 must have IPsec making it more secure than IPv4. This feature has now been made optional. IPsec, Internet Protocol Security, is a framework of open standards for helping to ensure private, secure communications over Internet Protocol networks, IP networks, through the use of cryptographic security services. IPsec is an end-to-end security scheme operating in the network layer. While some other Internet security systems in widespread use, TLS and SSH, operate in the upper layers, IPsec can automatically secure applications at the IP layer. No broadcast. Though Ethernet and Token Ring are considered a broadcast network because they support broadcasting, IPv6 does not have broadcast support anymore. It uses multicast to communicate with multiple hosts. Mobility. IPv6 was designed keeping mobility in mind. This feature enables hosts, such as a mobile phone, to roam around in different geographical areas and remain connected with the same IP address. The mobility feature of IPv6 takes advantage of auto IP configuration and extension headers. Extensibility. One of the major advantages of the IPv6 header is that it is extensible, adding more information in the option part. IPv4 provides only 40 bytes for options, whereas options in IPv6 can be as much as the size of the IPv6 packet itself. What is the IPv6 packet, you ask? You came to the right place. An IPv6 packet is the smallest message entity exchanged via the Internet Protocol across an IPv6 network. But stay with me here. The packets consist of control information for addressing and routing, and a payload consisting of user data. The control information in IPv6 packets is subdivided into a mandatory fixed header and optional extension headers. The fixed header starts an IPv6 packet and has a size of 40 octets, which means 320 bits. Its format is shown in the slide. Version is constant 6. Payload length is the size of the payload in bytes, including any extension headers. Hop limit replaces the time to live field in the IPv4. Well, I think source address and destination address fields are fairly obvious. Extension headers carry optional Internet layer information and are placed between the fixed header and the upper layer protocol header. 128-bit IPv6 addresses are written using hexadecimal, as opposed to dotted decimal back in IPv4. Because a hexadecimal number uses 4 bits, this means that an IPv6 address consists of 32 hexadecimal numbers. These numbers are grouped in 4s, giving 8 groups or blocks. The groups are written with a colon as a separator. An IPv6 address example is shown in the slide. So because of the length of the IPv6 addresses, various shortening techniques are employed. The main technique being to omit repetitive zeros, as shown in the example. So as I mentioned before, in IPv4, an address is split into 2 components, right? A network ID and a host ID. This was done initially using address classes, and then later using subnet masking. In the unicast addressing of IPv6, it's done in the same way. The first step is to split the address into 2 parts. The address is split into 2 64-bit segments. The top 64 bits is a network ID, and the lower 64 bits is the host ID. The most significant 64 bits are used for routing, and the least significant 64 bits identify the address of the interface or host. This block is derived from the actual physical or MAC address in practice. So if we look at the most significant 64 bits in more detail, we can see that it's split into 2 blocks of 48 and 16 bits. Now, the least significant 16 bits are used for subnets on internal networks and are controlled by a network administrator. The most significant 48 bits are used for the global network addresses and are used for routing over the Internet. Dynamic Host Configuration Protocol, DHCP. Now, it's a protocol used to provide automatic and central management for the distribution of IP addresses within a network. It's also used to configure the proper subnet mask, default gateway, and DNS server information on the device. In most homes and small businesses, the router acts as the DHCP server. In large networks, a single computer might act as a DHCP server. In short, the process goes like this. The device, the client, requests an IP address from a router, the host, after which the host assigns an available IP address to allow the client to communicate on the network. So let's look at some of the advantages of using DHCP. A computer or any other device that connects to a network, local or internet, must be properly configured to communicate on that network. Makes sense? Since DHCP allows that configuration to happen automatically, it's used in almost every device that connects to a network, including computers, switches, smartphones, gaming consoles, you name it. Now, because of this dynamic IP address assignment, there's less of a chance that two devices will have the same IP address, which is very easy to run into when using manually assigned static IP addresses. Using DHCP also makes a network much easier to manage. From an administrative point of view, every device on the network can get an IP address with nothing more than their default network settings, which is set up to obtain an address automatically. So that's easy, gives them nothing to call the help desk about. The only other alternative is to manually assign addresses to each and every device on the network. You're not getting paid enough to do that. So because these devices can get an IP address automatically, they can move freely from one network to another, given that they're all set up with DHCP, and receive an IP address automatically, which is super helpful with mobile devices. Now, as a cybersecurity expert, you should know one more thing about the DHCP mechanism. The first device which replies to a DHCP discover request decides the configuration of the client. There is not any mechanism to authenticate the DHCP server. Similarly, a DHCP server tries to reply to all the DHCP requests, and again, there is no authentication mechanism for the clients who request an IP. You get it? I think you do. What if a hacker replies before the real DHCP? Or what if a client sends a lot of DHCP discovery requests by changing the MAC address each time? So let's have a look to see how a DHCP mechanism works in detail. Once a device is turned on and connected to a network that has a DHCP server, it will send a request to the server called a DHCP discover request. After the discover packet reaches the DHCP server, the server attempts to hold on to an IP address that the device can use and then offers the client the address with a DHCP offer packet. Once the offer has been made for the chosen IP address, the device responds to the DHCP server with a DHCP request packet to accept it. After which, the server sends an ACK packet that's used to confirm that the device has that specific IP address and to define the amount of time that the device can use the address before getting a new one. If the server decides that the device cannot have the IP address, it will send a NAC. Let's see the DHCP server mechanism in Wireshark. So Wireshark is already embedded into Kali and it's ready to use. In addition, I'd also like to show you how to download and install it in a Windows system. So right now I'm in a Windows 8 system. Open the internet browser and search for Wireshark for Windows, using those as the keywords. First link is the download page of wireshark.org. So let's click it. My Windows is 64-bit, so I'll download the 64-bit, which is the latest stable version. Click it and save the installer. Now it takes less than a minute unless your connection is a mess. You might want to look into that. Just kidding. Click to run it. The setup wizard opens. Okay, so simply it's a next, finish installation. No need to change anything. Wait until the installation finishes. Okay, so check this to run Wireshark now and click Finish. And welcome to the Wireshark and Windows interface. So now I will show you the DHCP mechanism in Wireshark. So let's run Wireshark, and you can see that it's listing the packets received by ETH0. So to demonstrate the DHCP mechanism, we need to ask for an IP address over at the DHCP server. From the bottom right corner, right-click to the network icon and select Open Network and Sharing Center. Click Ethernet 0 and then Properties. You'll have to scroll down a little bit and double-click IP version 4. And as you see here, the IP address is manually set for my Windows 8. So to start a DHCP request, I'll choose Obtain an IP address and DNS server address automatically. Those are my options. Now, before I click OK, I'll go to Wireshark and restart capturing by clicking the green button on the toolbar. So now Wireshark Windows will be cleaned. Continue without saving. So now go to the network status window and click OK. And we can close all the networking windows. So Wireshark captured the packets. Well, it's still capturing, but let's go to the top of the list to find the DHCP packets. So here the DHCP Discover packet is right here at the top of the list. When we look at the ports in the UDP header, we see that the port 68 is used to send DHCP Discover packets. So let's go back to the filter box and type UDP port equals 68. And now we have the DHCP packets only. So the first packet is DHCP Discover. And as I mentioned before, it's broadcast. Source IP is all zeros because we don't have an IP address at the moment. Destination IP is all ones, 255.255.255.255 because it's a broadcast packet. And right here is Bootstrap Protocol, which is an application layer protocol used by DHCP mechanisms. The second packet is a DHCP offer packet sent by the DHCP server, 172.16.99.254 to the Windows system. Destination IP is 172.16.99.233, which is offered to the DHCP server. So in here, the destination MAC address is important. That's what's going to be targeted according to the MAC address. So as you see, the destination MAC address of the DHCP offer packet is the same as the source MAC address of the DHCP Discover packet. Now the third packet is the DHCP request sent by the Windows system. It's still a broadcast packet and the source IP is still all zeros. The message is request and the requested IP address is an option 50. So if you expand it, you see the requested IP address. And it's the same as the offered IP address, 172.16.99.223. The last packet is DHCP ACK, sent by the DHCP server to the Windows system. This packet completes the DHCP mechanism successfully. So from now on, the IP address of our Windows system is 172.16.99.223. Internet Control Message Protocol, ICMP, is an error reporting protocol that network devices like routers use to generate error messages to the source IP address when network problems prevent delivery of IP packets. ICMP messages are sent in several situations. For example, when a datagram cannot reach its destination, when the gateway does not have the buffering capacity to forward a datagram, and when the gateway can direct the host to send traffic on a shorter route. The Internet Protocol is not designed to be absolutely reliable. I'll explain why. Hold on. The purpose of these control messages is to provide feedback about problems in the communication environment, not to make IP reliable. There's still no guarantees that a datagram will be delivered or a control message will be returned. Some datagrams may still be undelivered without any report of their loss. The higher-level protocols that use IP must implement their own reliability procedures if reliable communication is required. So the ICMP header starts after the IPv4 header. All ICMP packets have an 8-byte header and variable size data section. The first 4 bytes of the header have a fixed format, while the last 4 bytes depend on the type and code of that ICMP packet. ICMP type and code in the header identifies the control message. Some of the ICMP control messages are shown in this slide. So ping is the most well-known application of the ICMP. It operates by sending ICMP echo request packets to the target host and then waiting for an ICMP echo reply. Some routers and firewalls are configured to not pass ICMP echo requests or echo reply requests. Attackers sometimes try to map out remote networks by pinging all the possible addresses and collecting replies. So blocking this type of traffic at the perimeter is fairly common. Just because you do not receive a reply to a ping does not necessarily mean that the host is not available. Traceroute is a computer network diagnostic tool for displaying the route or path of packets through the Internet between your computer and a specified destination computer. It also measures the amount of time each hop took. When you run the utility, it initiates the sending of a packet, including in the packet a TTL, a time-to-live value, which is also known as a hop limit. As the packet passes through a router, the TTL is decremented until when the TTL reaches 0, the packet is destroyed and an ICMP time exceeded message is returned. Traceroute works by setting the TTL for a packet to 1, sending it towards the requested destination host, and listening for the reply. When the initiation machine receives a time-exceeded response, it examines the packet to determine where the packet came from. So this identifies the machine 1 hop away. Then the tracing machine generates a new packet with TTL2 and uses that response to determine the machine 2 hops away, and so on. The command traceroute is available on many modern operating systems. On Unix-like systems such as FreeBSD, macOS, and Linux, it's available as a command line tool. On Unix-like systems, Traceroute sends, by default, a sequence of UDP packets. Traceroute is also graphically accessible in macOS within the Network Utility Suite. In Microsoft Windows, it's named Traceroute. In Windows, Traceroute sends ICMP echo requests instead of UDP packets. For IPv6, the tool sometimes has a name Traceroute 6 or Traceroute 6. Let's look how the Traceroute command operates in our host machine and virtual machines as well. So I'm on my host machine. This is Mac OS. And I'll open a terminal screen, Command Space to open the Spotlight search bar, and type terminal. Start the terminal app, and now I'm on a terminal screen. Traceroute is the command I'll use. So if you run it with no parameter, you get a brief help about the usage of the command. So now let's run the command with a target host. We timed out in the first hop. And in the second one as well. Way it happens, no worries. And yes, here are the other hops. This is the path that the packets follow from my host machine to the target web server. In Mac OS, you can also trace the packets with a graphical UI, which I mentioned before. So go to the Network Utility tool, press Command and Spacebar once more to open Spotlight, and type Network Utility and find it and open it. There's a Traceroute tab in the Network Utility window. Just type the target host and click the Trace button. Let's see how it all works in Kali. So now I'm in Kali, and I have a terminal screen open. Type Traceroute and hit Enter. So you'll see the help for this particular command, and it's a bit more detailed than the one in Mac OS. So now I want to show you the network configuration of my Kali. Go to Kali Settings, click Network Adapter, and as you see, we run Kali in NAT mode, where the host machine, Mac, provides network address resolution, we'll talk about that soon, for all network traffic, and Kali shares the IP address of the host. Now I want to test the network connection first. So I'll ping the Google DNS 8.8.8.8, and right, that's no problem at all. You can use Control-C keys to end the ping command. Just don't use Control-L. Okay, now I'll run the trace route with the target host in Kali. The first hop is a gateway prepared by VMware for my virtual machines. And as you can see, all the other hops are blocked. We cannot trace packets from the VM in NAT mode. So let's have a look at the traceroute command options once more. Here there's an option, uppercase T, which sends TCP SYN packets. Now I'd like to try the command once more with this option. Okay, so we have the first and the last hop this time. So now I want to show you the command in a Windows system. Here is my up-to-date Windows 8 system. It has an IP. Check the connection, ping, and yes, the network is running. Good, just where we want it. Let's look at the network details first. From the Network and Sharing Center, click Ethernet 0, and then the Details button, and here are the details. Default gateway is 99.2, DHCP is 99.254, as you know. These are the devices prepared by VMware for our NAT network. So now I go to the settings of the VMware Fusion. In Network Adapter, we confirm that the VM is in NAT network mode. Now I'm in the command prompt. As I mentioned, the command is Traceroute in Microsoft Systems. So write down the target host and press Enter. So the first hop is, again, the gateway. And just like in Kali, since this VM is also in NAT mode, the requests for other hops are timed out. So while the command is running, I'd like to show you the command help. So just type Traceroute and hit Enter. So we didn't enter the host this time, and here's a usage of the Traceroute command. Trace completed, and there is no result given, as expected, because we're in NAT mode. I know you knew that, but I just wanted to make sure. So now I'm going to run my Windows VM in bridge mode and try the command once more. And once again, click the hardware settings icon on the menu bar of VMware Fusion and select Network Adapter. So I'm using Wi-Fi to connect to the internet right now, so I choose Wi-Fi under the bridged networking section. Now this is the IP address assigned by the DHCP. and the subnet mask of the network, again, is set by DHCP. So we'll see how the DHCP works. Just stay with me here. So as you see in the Network and Sharing Center window, the active network disappeared as soon as I changed the network adapter of the VM. In a second, the new network is activated. Click Ethernet 0 and look at that, the Details button. So click on that to see the network settings, and those are the new ones. So now we're in the 192.168.12.x IP block. And we have a different DHCP and gateway run by the network admins of my office building. So let's go back to the command prompt and trace the route of the packets once more. So first I want to check the network, as I always do. So I'll ping the Google DNS, and yes, we have the internet connection. So now is the time to trace the route. The first request is timed out. Remember, the results of my host machine, right? The second request timed out as well. And here are the other hops. We now have the results. So now we're in the fourth layer of the OSI reference model, the transport layer. Welcome to the layer of TCP. The transport layer is the level at which system reliability and quality are ensured. The basic function of the transport layer is to accept data from the layer above, split it up into smaller units, pass these data units to the network layer, and ensure that all the pieces arrive correctly at the other end. Okay, so now let's look at the functions of the transport layer in detail. Service point addressing. Transport layer header includes service point address, which is the port address. This layer gets the message to the correct process on the computer, unlike network layer, which gets each packet to the correct computer. Segmentation and reassembling. A message is divided into segments. Now each segment contains a sequence number, which enables this layer to reassemble the message. The message is reassembled correctly upon arrival at the destination and replaces packets which were lost in transmission. Connection control. It includes two types. Connectionless transport layer. Each segment is considered as an independent packet and delivered to the transport layer at the destination machine. Connection-oriented transport layer. Before delivering packets, connection is made with the transport layer at the destination machine. Flow control. In this layer, flow control is performed end-to-end. The rate of data transmission between two nodes must sometimes be managed to prevent a fast sender from transmitting more data than can be supported by the receiving data buffer, causing a buffer overrun, and we don't want that. Error control. Error control is performed end-to-end in this layer to ensure that the complete message arrives at the receiving transport layer without any error. Error correction is done through retransmission. On the Internet, TCP and UDP provide the services for most applications. Coming up next, we'll look at all the other details of the transport layer under TCP and UDP topics. The Transmission Control Protocol, TCP, provides a communication service at an intermediate level between an application program and the Internet Protocol. It provides host-to-host connectivity at the transport layer of the Internet model. TCP works with the Internet Protocol, IP, which defines how computers send packets of data to each other. Together, TCP and IP are basic rules defining the Internet. TCP is a connection-oriented protocol, which means a connection is established and maintained until the application programs at each end have finished exchanging messages. It determines how to fragment application data into packets that networks can deliver, sends packets to and accepts packets from the network layer, manages flow control, and because it is meant to provide error-free data transmission, handles retransmission of dropped or garbled packets, as well as acknowledgement of all packets that arrive. Let's see the connection-oriented error-free communication of TCP in an example. When a web server sends an HTML file to a client, it uses the HTTP protocol to do so. The HTTP program layer asks the TCP layer to set up the connection and send the file. The TCP stack divides the file into packets, numbers them, and then forwards them individually to the IP layer for delivery. Although each packet in the transmission will have the same source and destination IP addresses, packets may be sent along multiple routes. The TCP program layer in the client computer waits until all of the packets have arrived, then acknowledges those it receives and asks for the retransmission on any it does not, based on missing packet numbers. Then assembles them into a file and delivers the file to the receiving application. The TCP three-way handshake is the method used by TCP to set up a connection. TCP's three-way handshaking technique is often referred to as SYN, SYNAC, ACK, because there are three messages transmitted by TCP to negotiate and start a TCP session between two computers. This three-way handshake process is also designed so that both ends can initiate and negotiate separate TCP socket connections at the same time. That means the connection is full duplex. Oh, you know what? We have to take a break at this point and talk about TCP flags. There are 1-bit flags in TCP headers, which are called TCP flags. TCP flags are used within TCP packet transfers to indicate a particular connection state or provide additional information. Ignoring ECE, CWR, and NS flags for now, there are basically 6 TCP flags. The SYN, or synchronization flag, is used as a first step in establishing a three-way handshake between two hosts. Only the first packet from both the sender and the receiver should have this flag set. The ACK flag, which stands for acknowledgement, is used to acknowledge the successful receipt of a packet. The RIST flag, which stands for reset, gets sent from receiver to the sender when a packet is sent to a particular host that was not expecting it. The FIN flag, which stands for finished, means there is no more data from the sender. Therefore, it is used in the last packet sent from the sender. The PSH flag, which stands for push, is somewhat similar to the URG flag and tells the receiver to process these packets as they are received instead of buffering them. The URG flag is used to notify the receiver to process the urgent packets before processing all other packets. So every legitimate TCP connection begins with a TCP three-way handshake, which is used to exchange sequence numbers so that lost packets can be retransmitted and packets can be placed in the proper order. If machine A wants to initiate a connection to machine B, it will start by sending a TCP packet with the SYN control bit set. This packet will include an initial sequence number, which I'll call here ISNA, because it comes from machine A, which is 32 bits long and typically generated in a pseudo-random fashion by the TCP software on machine A. The ACK number, another 32 bits in the TCP header, is typically set to 0 because it is ignored in this initial SYN. Some operating system variants may make this ACK number non-zero, but either way, it's ignored by the destination machine. So if the destination port is open, that is, there is something listening on that port, it must respond with a SYN ACK packet back, a packet that has both the SYN and ACK control bits set at the same time. This packet will have a sequence number of ISNB, a pseudo-random number assigned by machine B for this connection. The SYN-ACK packet will have an acknowledgement number of ISNA plus 1, indicating that machine B has acknowledged the SYN packet from machine A. To complete the three-way handshake, Machine A responds with an ACK packet which has a sequence number of ISN A plus 1. It's the next packet, so the sequence number has to change from the value in the original SYN packet. The acknowledgement number field is set to ISN B plus 1, thereby acknowledging the SYN ACK packet, right? So we have now exchanged sequence numbers. All packets going from A to B will have increasing sequence numbers starting at ISN A plus 1, going up by a value of 1 for each byte of data transmitted in the payloads of A to B packets. Likewise, all responses back from B will have sequence numbers starting at ISN B plus 1 and going up for each byte of data from B to A. In essence, we have two streams of sequence numbers in this series of packets, one from A to B, originally based on ISN A, and the other from B to A, originally based on ISN B. Perfect. A TCP segment consists of a segment header and a data section. The TCP header contains 10 mandatory fields and an optional extension field. The optional field is the options field, which is the last field seen on the slide. The TCP header includes a source port and destination port, each 16 bits in length. The source port is the port on the originating machine that emitted the packet. The destination port indicates the port on the target machine the packet should be delivered to. The sequence number and an acknowledgement number allows TCP to track a series of packets to make sure they arrive reliably and pretty much in order. No, absolutely in order. If a packet is lost, TCP will retransmit it. If packets arrive out of order, TCP will adjust them to make sure that they are delivered to the destination services in the proper order. Data offset specifies the size of the TCP header in 32-bit words. The minimum size header is 5 words, and the maximum is 15 words. There is also TCP control bit space, also known as flags, which are incredibly important for tracking the state of a given TCP connection. As you know, we talked about them a few minutes ago. Of course, if you didn't take a break, it was a few minutes ago. But whatever you do, just don't spill on the keyboard. Now, TCP senders use a number called window size, which is in bytes by default, to regulate how much data they send to a receiver before requiring an acknowledgement in return. So if the window size becomes too small, network data transfer will be unnecessarily slow, while if the window size becomes too large, the network link can become saturated or the receiver may not be able to process incoming data quickly enough, also resulting in slow performance. Windowing algorithms built into the protocol dynamically calculate size values and use this field of the TCP headers to coordinate changes between senders and receivers. A full duplex communication is established. UDP is another protocol of transport layer, layer 4, used primarily for establishing low latency and loss-tolerating connections between applications on the Internet. TCP has emerged as a dominant protocol used for the bulk of Internet connectivity owing to its services for breaking large data sets into individual packets, checking for and resending lost packets, and reassembling packets into the correct sequence. But these additional services come at a cost in terms of additional data overhead and delays called latency. In contrast, UDP just sends the packets, which means that it has a much lower bandwidth overhead and latency. But packets can be lost or received out of order as a result, owing to the different paths individual packets traverse between sender and receiver. So UDP uses a simple connectionless communication model with a minimum of protocol mechanism. It has no handshaking dialogues and thus exposes the user's program to any unreliability of the underlying network. There is no guarantee of delivery, ordering, or duplicate protection. UDP is suitable for purposes where error checking and correction are either not necessary or are performed in the application. UDP is an ideal protocol for network applications in which perceived latency is critical, such as gaming, voice, and video communications, which can suffer some data loss without adversely affecting perceived quality. In addition, since it's transaction-oriented, suitable for simple query response protocols such as the domain name system or the network time protocol. The UDP header is pretty simple. It consists of 4 fields, each of which is 2 bytes, 16 bits. The use of the fields checksum and source port is optional in IPv4. Are you surprised to hear that the source port is optional? But don't be, because, as you know, a UDP packet does not expect to get a reply in general. And again, since UDP doesn't care about the errors, the checksum field is, again, optional. Source port identifies the sender's port, and the destination port identifies the receiver's port as well. And the length field specifies the length of the UDP header and data in bytes. So now's a good time to compare the 2 protocols, UDP and TCP, as a brief summary. Most services on the Internet use either TCP or UDP, which are carried end-to-end across the network using IP, either IPv4 or IPv6. The Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, are very different. TCP is a connection-oriented protocol which tries to ensure reliable, in-order delivery of packets. If packets are lost, TCP automatically retransmits them. If they arrive out of order, TCP will resequence them before handing them up to an application. UDP is connectionless. The UDP software makes no attempt to associate streams of packets together. So as far as UDP is concerned, each packet is completely independent, unrelated to other packets. No attempt is made by UDP for retransmission or resequencing. If a packet is lost via UDP, it's up to the higher layer application to resend it. And finally, we're in the application layer. Now, if you remember, I mentioned before, for the ease of use, the last 3 layers, session layer, presentation layer, and application layer, are thought of together as the application layer. As you know, these 3 layers are already a single layer in the TCP IP reference model. So the application layer contains the communications protocols and interface methods used in process-to-process communications across an Internet Protocol computer network. The application layer only standardizes communication and depends upon the underlying transport layer protocols to establish host-to-host data transfer channels and manage the data exchange in a client-server or peer-to-peer networking model. So let's have a look at some important protocols of the application layer. The often used analogy to explain the domain name system is that it serves as the phone book for the Internet by translating human-friendly computer host names into IP addresses. Simply, DNS is a directory of names that match with IP addresses. As you may know, each device connected to the Internet has a unique IP address which other machines use to find the device. DNS servers eliminate the need for humans to memorize IP addresses, such as 212.80.75.134. Think about the websites you visit every day, Google and YouTube, Facebook, Twitter, etc. Without DNS, we would have to reach these sites by using their IP addresses instead of their names. I think remembering the names is so much easier than remembering the strange numbers. But it's still possible to reach the computer with that strange number string as well. Now, DNS deserves to have far more time spent on it. It could be a whole course in and of itself. But I just want to explain it simply without going too deep. So when you enter the URL, such as www.google.com, into the web browser, the request is not directly sent to the Google servers. Instead, the request goes to the DNS server that uses a lookup table to determine the IP address of the website that is being requested. Then it forwards this information to the proper servers and returns the information requested to your specific browser. DNS server is a computer server which contains a database of public IP addresses and their associated host names. It translates those common names to IP addresses as requested. DNS servers run special software and communicate with each other using special protocols. DNS is a client-server network communication system. DNS clients send their requests to and receive the responses from DNS servers. The requests containing the name and resulting in an IP address being returned from the server are called forward DNS lookups. The requests containing IP addresses and resulting in the names are called the reverse DNS lookups. The DNS directory that matches name to number isn't located all in one place. Pretty much like the Internet itself, the directory is distributed around the world, stored on domain name servers that all communicate with each other on a very regular basis to provide updates as well as redundancies. With more than 332 million domain names listed by the end of 2017, a single directory would be very large indeed. So when you type mail.google.com into your browser sends a query over the Internet to find the website. It's a query seeking to match the domain name with its corresponding IP address. So let's follow the path of this question over the Internet infrastructure. The first server your query interacts with is the DNS resolver, which can be operated by your ISP, Internet Service Provider. A resolver is basically responsible for initiating and sequencing the queries that ultimately lead to a full resolution. Domain name resolvers determine the domain name servers responsible for the domain name in question by a sequence of queries, starting with the rightmost, in other words, top-level domain label. Assuming the resolver has no cached records to accelerate the process, which is the worst-case scenario, the resolution process starts with a query to one of the root servers. The root servers are running all over the world, and each one knows DNS information about top-level domains, or TLD, such as .com. So to begin answering your query, the resolver asks a root server for DNS information about .com. So there are 13 sets of root servers in more than 300 locations around the world. Each TLD DNS name server stores the address information for second-level domains within the top-level domain, .com in our example. The second-level domain is google.com. When your query reaches the TLD server answers with the IP address of the domain's name server, which will provide the next piece of the puzzle. So this is the final step of address resolution. The recursive resolver sends the query to the domain's name server. This DNS server knows the IP address for the full domain, mail.google.com, and that answer is returned to the recursive resolver. Now that the recursive resolver knows the IP address for the domain name in your query, the recursive resolver tells the browser what the IP address is. So finally, your browser can send a request to the website to retrieve the website's content using the IP address it just learned. This whole process might seem, complicated. It certainly sounds it to talk it out, but really takes very little time at all. Hypertext Transfer Protocol, HTTP, is an application protocol. Hypertext is basically structured text that uses logical links between nodes containing text. And HTTP is the protocol to exchange or transfer hypertext. So HTTP is a stateless protocol. That means no information is retained by either sender or receiver. It functions as a request-response protocol in the client-server computing model. A web browser, for example, may be the client, and an application running on a computer that's hosting a website may be the server. The client submits an HTTP request message to the server. The server, which provides resources such as HTML files and other content, returns a message to the client. The response contains completion status information about the request and may also contain requested content in its message body. So the most used HTTP request is GET. A GET request is designed to request server resources. With this type of request, the parameters are sent to the server inside the URL. A POST request is designed to request server resources as well as a GET request. Unlike a GET request, parameters are sent to the server inside the body of the request instead of the URL. Well, it's still possible to send the parameters inside the URL, but if you use a POST request, it's better to send parameters inside the body than inside the URL. So what's the advantage of sending parameters inside the body instead of the URL? Almost always, the traffic between the server and the client is logged on the server side. Such log files usually contain the URL. If you send the parameters in the URL, they are saved as clear text in your log files. So anyone who can see the log files can also see your sensitive parameters. You should use POST requests to send sensitive data. But please note that it's not enough for the privacy of the traffic, because any man in the middle who listens to the network will see the parameters even though they are inside the body of the request message. So you should encrypt your traffic, always. Now, the server, which provides resources such as HTML files and other content, returns a response message to the client. The response contains completion status information about the request and may also contain requested content in its message body. So every response has a 3-digit response status code, such as 200 OK, 302 found, etc. Now, HTTPS consists of communication over HTTP within a connection encrypted by TLS, Transport Layer Security, or its predecessor, SSL, the Secure Sockets Layer. The main motivation for HTTPS is authentication of the visited website and protection of the privacy and integrity of the exchanged data. So let's see how a typical encrypted connection between the server and the client is established. The client sends the information that the server needs to communicate with the client using SSL. This information contains the client's SSL version numbers, cipher settings, and session-specific data. The server then sends the information that the client needs to communicate with the server over SSL. The server also sends its own certificate. The client uses the information sent by the server to authenticate the server. So using all data generated in the handshake thus far, the client creates the pre-master secret for the session, encrypts it with the server's public key, and then sends the encrypted pre-master secret to the server. The server uses its private key to decrypt the pre-master secret, and both the client and the server perform a series of steps to generate the master secret. Then, they use the master secret to generate the session keys, which are symmetric keys used to encrypt and decrypt information exchanged during the SSL session and to verify its integrity. The client sends a separate message indicating that the client portion of the handshake is finished, and the server sends a separate message indicating that the server portion of the handshake is finished.